So we are, perhaps I should justify why we're talking about this particular infinite matrix. Well, firstly, what is the matrix again? So it's an infinite matrix, this way and this way. Square matrix, I guess. The rows are labelled by a Turing machine, M1, M2, M3, all possible Turing machines. Okay. Now we know they are countable. That was one of the theorems. So you just list all possible Turing machines, and they'd be your row headers, row identifiers in the matrix, and the column headers here, the column identifiers, if you like, they are the angular brackets of each of these. In other words, the label that is the description of each Turing machine. And the entries here for you interpret, like the A here, AH is short for accept, and what that means is, let's do an example. If Turing machine M1, if it has as input, so these are input strings, right? So if M1 has as input string angular bracket M3, it would accept. There's an A here. Now where I've got the dots, look on them as blanks. So you just have a blank entry in the matrix. So for example, if machine M4 has as its input string angular bracket M3, so that's the input string to this machine, it does not accept. So you just have a blank here. Well, I put a dot, just so it makes it less confusing. Right? So the entry, any one of these elements in the matrix, so the ijth, the ith row, jth column, will be an accept, an A, if the Turing machine Mi accepts this input string mj. Okay. Now get back to why are we doing this? Because it's a nice graphical way to show the contradiction. We had a kind of logical contradiction before. When D operates on the angular bracket D, it will accept D will accept angular bracket D if D does not accept angular bracket D, and D will reject angular bracket D if D accepts angular bracket D. Now that's a logical contradiction. What we're going to show now via these infinite matrices is a kind of pictorial contradiction, sort of more visual, if you like. It's an alternative way of coming to the same conclusion, that you've got this logical contradiction. Okay, all right. Well, now we're going to make a second infinite matrix where the row headers are the same, the column headers are the same, so they're all the same. But now the entries are different. These entries, the elements in the matrix, are interpreted differently from the case here. Here, in the second case, these entries, they're the accept or reject, A for accept, R for reject, for how the machine H would react given the ordered pair Mi, Mj, or angular bracket Mj. So the entry, these elements, the ith row, jth column, that's the value, accept or reject, of how H, the machine, Turing machine H, would decide on the input of the ith machine, Turing machine, the ith row here somewhere, and the jth column, and that's the string that goes in, and it's the description of the jth machine, and so the jth column somewhere, right? So, so this summarize the difference between the two entries, the two different matrices. In this case, the accept here just means that that machine will accept that input string. Okay, and in this case, these accept and rejects, the elements here, the infinite matrix, they are the results of the decisions, if you like, of machine H. Okay, given the ordered pair, Mi and angular bracket Mj. That's what it's saying here. All right. now we come to the crunch. We do the same thing. We just do this again, but we add. Well, it's implicitly there anyway. But we add Turing machine D, because D is a Turing machine, right? And remember, there's an infinite, countably infinite matrix. The number of rows is countably infinite number of Turing machines. And we proved that before, that the set of all Turing machines is countable. Okay. Now, since D is a Turing machine, it will have its row, right? And the description of D, it'll have its column, right? Now, what is this? All these entries here, what are they again? Well, it's the same as here, and this is how the machine H replies, the decision, accept or reject, of H. Okay, so whatever it is you have here, the D will be the opposite. Okay, but what do you have here? Right, that's you get a question mark, right? Just what do you have there? So you got yourself a contradiction. Yeah. So the contradiction occurs here because let's see. Make this clearer a bit. Yeah, again, Sipser is not. I didn't find Sipser clear on this point. Let's see. Okay, so D is the Turing machine. Okay, that's clear. Okay, so it must be one of these, because this is the list of all Turing machines. Okay, so it says this one. So here's the row of D, and all these R's and E's here. They're how H replies, and so whatever if you had H. Whatever it is here, will D just be the opposite. So what is actually here? It's not clear. So contradiction occurs here, point of the question mark, where the entry must be where the entry must be the opposite of itself. So whatever's here, it must be the opposite. And that's a sort of visual contradiction. Okay. So we've got yourself a contradiction, and this is me adding this. I mean, Sipser didn't bother. You've got yourself a contradiction. To him it was so obvious, I suppose, and therefore A sub Tm is undecidable, right? Because of that contradiction. So you go back to what you originally started with when you negated what you really wanted to prove, and you negate that. So you got a double negation of what you really wanted to prove. So not something is just something. and therefore ATM is undecidable. Ta-da! Right. Okay. Now, the last session pretty much, we will do even more damage. Like I was saying in the first session, we will now show the existence of a language that not only is it is undecidable, it's worse than that, it's Turing unrecognizable. You know, there's no machine that can even recognize the language. So now that language it's not ATM. That won't work, because we showed earlier that ATM, suffix TM is actually Turing recognizable. We proved that, right? So we have to find something else, but that'll be for next session.